loud and get it to Becky a little bit later today. A couple more queuing up in the waiting room, so let me admit those. I don't know, Jen, if you can see the waiting room at the top of the participant list, but
yep, I'll just keep adding people.
Yeah, if you, while I'm doing the introduction, if you don't mind catching that.
I'm going to just move this over the screen. There we go.
Jen, Carey asked a question about tallying total people.
Yes.
So we could probably, if you're out there in a group, we welcome everybody to this month's UNH Care seminar. I'll do an introduction in just a moment, but if you're out at a location with some other folks there, if you would like to put in the chat box how many is in your group, that'll help us kind of have a good idea of how many are joining us this morning. I think what I'll do now, if this is okay with my colleagues, I'll go ahead and introduce this month's speaker. I'm really excited. We have with us and providing a talk this afternoon, Dr. Michael Ainslie, who's a senior scientist at JASCO Applied Sciences in Germany and visiting professor at the Institute of Sound and Vibration Research at the University of Southampton in the UK. Michael holds degrees in physics from Imperial College and mathematics from Cambridge, and a PhD in seabed acoustics from the University of Southampton. He's author of the book Principles of Sonar Performance Modeling, and his research interests include sonar performance modeling and effects of sound on aquatic life. He's a convener of the ISO working group on underwater acoustic terminology and a member of the ANSI working group on bioacoustical terminology. So if you have any questions whatsoever about terminology, Michael's the guy to ask about this. I asked Dr. Ainslie if he would share kind of a fun fact, and I'm not going to go into all the details. I'm sure he would be glad to share this with you, but he shared a little story about how back when he was traveling to the US, I think to a bioacoustics meeting in San Diego, he had an interesting interaction with a US immigration agent when he was coming to the meeting, in which without providing a lot of details, in which his scientific moxie was probed a little bit once he introduced himself as a physicist. By a very what seemed to me a very well-informed and primary literature reading TSA agent. And so luckily Dr. Ainslie survived what I've coined the neutrino interrogation of 2012 to join us here today, and will share his science with us in a talk entitled Ocean Ambient Sound from Shipping and Baleen Whales, a multi-decade low-frequency soundscape of the Northeast Pacific. Michael, thanks for joining us today. We really appreciate you sharing your science with us.
Thank you, Dan, for the introduction and for the opportunity, giving me the opportunity to talk at your prestigious webinar series, and Jen, you too. Thanks to everybody also for joining, especially those who've joined at slightly perhaps in less than civil hours. I'll be talking about the soundscape of the Northeast Pacific Ocean. I see that in my title slide, the APL logo. That's the logo of APL UW Washington. Seems to have obscured the word Pacific in the subtitle, but that's what it says: soundscape of the Northeast Pacific. And it's about contributions from shipping and from baleen whales to that soundscape. And I will be pushing some of the accepted wisdom. I'll be pushing a little bit and testing the validity of that accepted wisdom of the soundscape. And you'll see what I mean as I say that. So by way of introduction, it's widely reported that in the Northeast Pacific, in the second half of the 20th century, there was a 10 dB increase in shipping noise at the frequencies shown in these two graphs. There are two different publications here, one from Rector Andrew published in 2002, showing a 10 dB increase, and another one a few years later by Mark McDonald, showing also a 10 dB increase in a similar location, both of them in California. And similar results have been shown also by others. So in terms of the talk, I'll start by introducing 4 measurement sites which we've been looking at. Oh, wait a minute, I say we, I haven't introduced my co-authors. So my co-authors are Rector Andrew at the University of Washington, Bruce Howe at the University of Hawaii, and Jim Mercer also at APL at Washington. So a lot of what I'll be saying, all the measurements that I'll be showing you, measurements of theirs. Hence being reminded by the 4 measurement sites. Sorry, Rex and Bruce and Jim for forgetting you if you're there. I'll be focusing on 2 questions. First one, why did the level increase by 10 dB? And secondly, why did the level stop increasing around the turn of the century? And then I'll come at the end of some dwell on some of the significance of the answers to those 2 questions. So these are the 4 measurement sites up and down the western coast of the USA. The 2 southern ones are both in California, that's Point Sur and the Nicolas Islands. The ones further north, the one I've labeled Oregon is at this boundary between Oregon and California. The one I've labeled Washington is the boundary between Washington and Oregon, somewhere around the boundary. That's enough. Oh, good. Next slide. The 2 questions then. The first one, why did the level increase by 10 dB? And the reason why that's an interesting question is because the shipping fleet only doubled in that time. The lower graph here shows the size of the global shipping fleet between 1965 and 2000. And, well, it actually goes beyond there, but these 2 vertical lines is when the 10 dB increase occurred. And there's a rough approximately doubling of the size of the fleet in that time, in terms of the number of ships. And I shall focus at the beginning on that first question. Towards the end, I'll start looking at, well, what's happening here? Why is the level apparently beginning to slow down when the number of ships continues to increase? So why did the level increase by 10 dB? A couple of quotations from McDonald's paper. Increase in commercial shipping are believed to account for the observed low frequency ambient noise increase, and a doubling of the number of ships alone would explain only 3 dB. Hence, an increase of roughly 7 to 9 dB is needed in the source level to be able to explain the observed increase in level. That observed increase is what you see on the right there, 9 to 11 dB, roughly read from the graph, versus 3 dB if one just calculates 10 log of the number of ships. And a more recent publication, I added this quote this morning because I was reading this paper over the weekend. There's a claim in this paper by Duarte and co-authors that over the past 50 years, this verbatim, increased shipping has contributed to an estimated 15 dB. So it's kind of going even beyond the 10 dB for which there is evidence, and making a claim about 15 dB for which I'm less sure about. But the 10 dB is fairly safe. That's consistent with both McDonald and Andrew's work. And here's the same graph again from Point Sur. This is from Andrew 2002. It's showing the red here, the 10 dB increase observed, and in blue the effect that you might expect from just 10 log times the number of ships. So illustrating the discrepancy between them. So McDonald points out that actually, okay, the number of ships might have doubled, but actually the ships themselves have got bigger, and the gross tonnage has increased by more than a factor of 2. And And if you actually take into account, and if you just assume that the noise is proportional to the tonnage instead of being proportional to the number of ships, then you get an estimate of 5.5 dB. But that is actually still 5 dB short of what we're looking for, even with the 5.5, even by assuming the proportionality with tonnage. Now, George Frisk assumed a square behavior, 20 log of GT, which is the same as 10 log of the square of tonnage. And if you do that, you do get the 11, very conveniently get the 11 dB that you're looking for. The Frisk paper presents no theoretical motivation for squaring the tonnage. So I'm not going to be looking at this any further. I'm going to focus on more along McDonald's ideas of proportionality with tonnage, which makes more sense to me. Here's some actual measurements. The ones on the left are what I will be calling low frequency sound, which is in the range 16 in the bands in the 16 to 32 hertz decidecade bands, and you show that these pictures clearly show 4 different locations. Each different color here is a different location. Each symbol represents 1 month. And you can see that they peak at certain times of the year, and basically in the late summer, in September and October, they peak at these, certainly the 2 sites you can see here labeled, which is the blue is D, which I believe is Point Sur, and the F is Ainslie, St. Nicolas. So it might be the other way around. It's not terribly important for this present purpose. And then on the right, you can see higher frequencies. Showing a more regular, almost sinusoidal pattern at some of these sites, the black one and the blue one there, especially. And here they peak not in the late summer, but in midwinter. In fact, they peak in late February or early March. And so the question is, does this behavior, and I think that this one's now zooming in on this, it's exactly the same information, but zooming in on a 20-month time series. The previous one was 12 years, I'm showing you. These are now 20 months. Each symbol is again 1 month. But now you can see more clearly on the right the sinusoidal pattern for the higher frequency sound. And this red one is an average of the 4 measurement sites. And on the left, is the low frequency sound, and again the red is again an average, and the red dotted line is an average of the average, so it's the mean value of the red curve. And here the difference in timing is is immediately noticeable. Here you've got a big peak with the long duration around this long period between August and November, compared with a more natural peak in the middle of the winter from the right-hand side picture. So again, what does this tell us? What information is this providing us? What clues is it telling us about the cause of the sound? Okay, so I started by saying that there was this widely reported 10 dB increase from ships. So I started looking at what would I expect from the ships, and basically what we did was we said. Worked out how many ships there were. We worked out roughly from knowledge of the average source level of a single ship, which has been measured multiple times in the 20th century. We added total energy produced, total acoustical energy produced by all of the ships together, assuming that they're all in deep water. And then worked out how much of that is trapped in deep water by knowledge of the soundspeed profile. We divide that total of trapped energy by the total ocean volume, which gives us the average energy density in the sea. And the energy density in the sea is very closely related to the mean square sound pressure. It's the global average of the mean square sound pressure that it actually represents, that average energy density. So you've got this idea there's lots of acoustical energy out there. You don't know where it is, but you have an idea of how much there is on average. And when you put this in the pot, what you get out is a relatively simple expression here that's proportional to the gross tonnage. This G here is the gross tonnage I was talking about before. So Mark Donald was on the right track when he was talking about proportionality with tonnage. It's inversely proportional to the volume. That's fairly obvious, but the volume is a constant, so it doesn't doesn't really change anything. It's proportional to the cube of the sine of the critical angle, and I'll explain more about that in a minute. This is crucial to understanding how much sound is trapped. There's a certain range of angles that are trapped in the sea. It's inversely proportional to the absorption coefficient in the seawater, and it's proportional for fairly obvious reasons to the amount of energy radiated, the amount of power radiated by each ship, which is represented by the source factor here. It's also inversely proportional to the source depth, so this is the nominal center of acoustical center of the sound from the ship. It's radiated sound. So I mentioned the critical angle, and remember that the amount of energy available is proportional to the cube of this quantity. If you imagine that your ship is up here, right at the surface, this represents the entire ocean volume down to 4 kilometers, and this is the sound speed profile. If the sound speed at the top is less than the sound speed at the bottom, which it often is, then you have a range of possible angles, which are represented by this ray and this ray, these two sound rays, within which all of the sound is trapped because it just carries on refracting up and away. It's basically enters a series of convergent zones in deep water. Anything steeper than this critical angle is reflected by the seabed and effectively lost to the long-range propagation, which is what we're interested in, looking at the contributions of sound from distant ships. And when you do that, remember this proportionality with the cube of the cube of the critical angle. Now, the critical angle depends on the surface sound speed, and the surface sound speed depends in turn on the temperature of the sea surface. And that sea surface temperature varies with season. It's lowest in March, highest in September. And therefore, the critical angle also varies with season. The critical angle is highest in March, and so we expect a peak in the sound levels in March. And I can't spell afternoon here, but there is a well-known afternoon effect that was discovered in the 1930s, or explained in the 1930s rather. It was discovered before then. It was a well-known effect from sonar operators that in the afternoon their sonar stopped working. Why? Because the sea surface had warmed up, and it was Ainslie and Batchelder who noticed that, who explained the behavior, explained why sonar stopped working in the afternoon because of the high surface temperature. Well, here what we have is the same effect. We have the high surface temperature increasing it's basically, if it goes beyond this value, the sound speed shifts, then there's no distant paths, and the ocean would, under those circumstances, quieten. Not suddenly, because it happens over a period of months, but certainly I would expect that there to be much less noise, much in a warm, in a very warm summer than in a cold winter. And here is these three red lines are the predictions using the formula I showed you, knowing the known dependence of temperature with season, for three different assumptions about the average temperature, 12, 14, and 16 degrees. It's a prediction for 80 hertz. And then the symbols on this graph are the measurements at three different frequencies. And the measurements are for 50 hertz, 80 hertz, and 125 hertz. So the one that we're interested in is actually this one here, the red one. And you can see that the time dependence is roughly the same. Roughly the predicted time dependence here, it roughly corresponds with the measured time dependence, which is comforting. There is a mismatch in level. The theoretical value is about 5 dB higher than the measured value. One of the reasons for that is that this calculation assumes that all of the ships are in deep water all of the time, when in reality, many will be either in port or in shallow water, and that would bring down this prediction if we only knew how many ships were in deep water. That explains part of the discrepancy, though not all of it. So, okay, now armed with this extra information, this is the same formula as I showed you before, and in this table, I've actually added a new column. Before I had the increase of 10 dB in the frequency range 16 to 32 hertz. I didn't talk about high frequencies, but the higher frequencies are the ones where we see this regular pattern. Remember that the regular sinusoidal pattern in the time dependence. Those were not at these frequencies. These were at these frequencies in the range 50 to 120 hertz, where we see an increase of about between 3 and 8 dB. Now, in this formula gives us an predicted increase of just less than 5 dB, which is well within the range of the measurements in that same frequency range. So here we see exactly the same graph as I showed you earlier, but I was cheating. I deliberately highlighted this region here where you get the 10 dB, which I knew was actually not caused by the ships. And now if I'm more honest with you, I show the part that is caused by the ships is this region here. And this was the 328 dB that I mentioned. And this blue arrow is showing the 5 dB increase from the shipping. So actually, there is no missing 7 dB as is claimed in some papers. It's the predicted increase is about 5 dB. The measured increase is about 5 dB. So that's the first bullet here. That the 5 dB increase is fully explained by the theory. There is no deficit of 7 to 9 dB. But what I haven't been able to do with this simple theory is explain what does cause the 10 dB increase. And so to answer that question, it's worth looking in more detail at these spectrograms I showed you. And if you look at the frequency range that we're talking about, between 16 and 30 hertz, these frequencies down here, you see these features which show the sharp increase in the summer that we're talking about, and basically barren in the winter. And if you look at the paper by Julie Burtenshaw, published in 2004, she ran a blue whale detector on these measurements, exactly the same time series. And she shows that basically this blob here, this blob here at the St. Nicolas side, basically correlates almost perfectly with blue whale detection. So these are blue whales contributing to the low frequency sound between 16 and 32 hertz. And here from the same Burtenshaw paper, she shows that actually she actually has 2 extra sites that I don't have access to. She's got a total of 6 different sites up the same coast, up to Vancouver Island here. And what you see is as you go further and further north, the peak from the blue whales, these are blue whale detections. They become less intense, but and more distributed over time, but they also get delayed. So what you can see basically is the effect of the whales, at least this is my understanding of the correct interpretation. These whales are migrating northwards from Southern California. They start in Chile. They reach Southern California by July, and they keep migrating northwards, reaching Vancouver Island around December time, and they stay there apparently until through the winter months. So now, same picture I showed you before, we can understand in terms of ships at high frequency. This red line is basically the trend that you expect, the sinusoidal behavior I showed you from the temperature variation in the shipping sound. This feature here corresponds almost exactly with the blue whale season from the Burtenshaw paper. This large red peak here, and these, especially at the blue site D, which is Nicolas, I believe. It's point solar. I've labeled it here. That's handy. So point solar, blue ones are point solar, the jitter ones are census. Okay, I don't think there's anything more to be got from this view graph. Just revisiting the old one. So this is also revisiting the previous graph, but in the light of the new knowledge that got shipping contributing to this blue frequency range, primarily blue whales contributing to this lower frequency range. What's interesting here is that the increase, this is from McDonald's paper, there's a clear increase in what looks like a large peak here of fin whale. This is about 20 hertz, which is typically a fin whale fundamental frequency. And that frequency is reduced in the more recent measurements by at the same site in 2006 to about 17 hertz, which corresponds more closely, so I understand, to blue whales. So I imagine that both of these are actually a mixture of blue whales and fin whales, but the mixture seems to have changed over time. Okay, and one more feature of this graph is that there is a harmonic of the blue whale here. So we've got the 16 hertz fundamental. There's also a 32 hertz peak, which is here from the blue whales, and a 48 hertz peak at the third. Sorry, the next harmonic up is 48 hertz from the blue whale. Is actually in the 50 hertz band, which I described earlier as being from ships, and I actually think it's a contribution of 50 hertz from both the whale and the shipping. So I kind of recalibrated the frequency range, and I'm now suggesting that this frequency range, 63 hertz up to 125, is the main one that's dominated by shipping. What I've drawn on here by hand, that just appeared from below, is the 9065 measurement, but just added with 5 dB added to this hump here, which I believe is caused by ships. And what you see by that, but when you do that, is that you get it starts to interfere, if you like, with this peak here, which, and I'm speculating now, but my speculation is that there might have been masking from the lower frequencies here from the ships, masking these calls here at 20 hertz, and perhaps that's why the whale shifted to a lower frequency, or perhaps it's because these are fin whales and these are blue whales. But anyway, there is this is what happens if you add 5 dB to the 9065 measurement. So remember that the question I've been asking all along was, why did the level increase by 10 dB? Well, it has nothing to do with the number of ships, because it didn't. The 10 dB increase did not occur in the frequency range which is dominated by shipping. There are a number of possible explanations. There's basically 3 possibilities. Either the whales are making the sound, there are far more of them, or each whale is making far more sound, or perhaps, and most likely, it's a combination of the 2, that there are more whales and each whale. Each individual is making sound on average, I should say. So, for example, it could be a larger proportion of making the sounds, making them longer. What's this one about? This one is looked at. Okay, this is thinking about what might cause that 10 dB increase. There is mention in the literature of a 6% increase in population annually. I don't know whether that can be sustained over multiple years, or whether it has been sustained. But if it's sustained, it would result in a factor of 6 increase over 30 years, which would give you an 8 dB increase in the frequency range that we're thinking of. And we're looking for 9 to 11 dB. So maybe, and again, just pure speculation, maybe there is also an increase in source level as the whales competed with either themselves because they're being more noisy, or perhaps because of the increased noise at those low frequency. Whatever reason, they might have raised their voices slightly to give an extra 2 dB. But basically, if you just go by the 6% increase reported by Barlow and by Burtonshaw, you get 8 dB. Actually, I should rephrase that. I'm not sure that Barlow says this. It's Burtonshaw that reports the 6%. Her paper cites Barlow. I haven't actually seen Barlow's work, just in case. Barlow happens to be listening in. He might be. Who knows? Okay, and that brings me to my second question. Why did the level stop increasing while the shipping fleet continues to grow? Well, again, this is a red herring. This isn't found from ships. So this saying there's been no significant evidence of an increase in traffic noise between 1994 and 2006. So this is showing basically that the 10 dB increase, order of magnitude, has not changed. There's some sites, at some sites there's a small increase, at some sites there's a small decrease, but it basically stays at 10 dB. From the number of ships, I would expect another 1 dB if it were coming from ships, but like I've already said, I don't really think that's the case. I think the sound is coming from whales. If you look at the blue whale abundance estimates of the past 30 years, you see that there's a hint of a small decline, but actually it's more honest to say that it's stable. That the error bars here are so large that it's basically constant stock at around 2000 since the 1990s. So it's not surprising then that the levels have stayed roughly constant since the 1990s. To conclude then, we've got in the 63 to 63 to 125 hertz bands, we've got a peak in the winter, dominated by ships, the sound from ships. We've got an observed 5 dB increase in 34 years. We've got a predicted 5 dB increase in the same time. There's no missing 8 dB from source level because the 10 dB increase is not in this band. We've got at the lower frequencies, we've got a highly seasonal behavior with a broad peak in the late summer. It's clearly dominated, at least now, by blue whale vocalizations. The observed 10 dB increase can only be explained really by speculation. I've already been there, but this next slide goes a little bit further into that speculation. Here's the same graph I showed you before, the population estimates. Here's the 6% growth estimate I mentioned before, with 8 dB. If you wanted to explain all the 10 dB just from growth, you'd need 8% per year. But if the animals are vocalizing more strongly, either frequently, loudly, or whatever, then perhaps the 8 dB is enough. There are also blue whales up there. They, unlike the blue whales, they show a fairly steady growth in population since the 1990s. This graph up here, and it's not terribly clear, perhaps. They start at the bottom left here at around 1500, just reading the graph, going up to about 7,000 or 8,000 in the late, in the 2010s. The fin whales make a strong peak at 20 hertz with the 40 hertz harmonic, so that might explain the this peak here, which I didn't refer to before. I pointed you at the 32 hertz peak, the 48 hertz. I didn't draw attention to the 40 hertz peak, but I'm doing so now. I'm suggesting that maybe that 40 hertz peak is coming from fin whales. And okay, on this graph here, even more speculation. What if we could write a formula like this, where the n here is the number of whales, the number of baleen whales vocalizing in any particular frequency band. If the level were equal to a constant plus 10 log of the number of whales, then effectively, if you knew what the constant was and you'd measured the level, you could then infer the number of animals. And in principle, then that would be the acoustical method for counting baleen whales. I'm not suggesting you can do that at one site. I don't think that this one site at Nicolas is anywhere near sufficient. You need multiple receivers, add them up and down the coastline to get an average value of the K, similar to what I was doing for the ships. And once it was calibrated, then use this acoustical measurement of the number of whales and compare it with the other methods for calculating measuring the number of whales, which also have high error bars. People, I know you'll all be thinking, but that's crazy. It'll never be very accurate. Well, of course it won't. It won't be accurate, but it'll give one more method for assessing the numbers for which we actually have very few reliable ways of counting. So it gives us one more box, is how I see it. And that is actually the end of my talk, apart from the references and a question slide. So I hope Ken's battery lasted out.
That's great. Thanks, thanks, Michael. It's a tremendous talk. I think what we may do at this point, we've got a nice pot of time that we can field some questions. So feel free to, if you have a question, unmute your mic and ask it, or you could put it in the chat window as well. And I'm sure Ainslie is more than willing to take a stab at your questions.
Can I go first? I have a question.
Go for it, Jen.
So I'm really happy, Michael. This was great because it was a fun story. And halfway through it, the whole time I'm sitting here for the first half, I'm like, fin whales, fin whales, fin whales. So I was happy to see those fin whales come in. One thing that I thought of that maybe would help your speculations was Anna Sorovic really showed a change in fin whale structure, both frequency and the structure. They were, I believe the structure caused their song to sort of have additional components. I can't remember the details, but I know that the structure along the coast of California and fin whales over the past few decades has changed. And I wonder if that may add some more meat to your speculations.
Yeah, I mean, it's one more piece of one more piece for the pot to try to explain. So far, I've been looking at the precise range of frequencies. It comes in only at the end. I mean, you need to know which animals are vocalizing and at which frequencies. That's certainly true. I agree with that. It does seem to be the case from Burtonshaw's work that most of the sound is from blue whales rather than fin whales. And to be honest with you, that surprised me as well. I was expecting more from fin whales. And I suspect that there's been a transition that back in the 1960s, I think that maybe there was a large contribution from fin whales based on the higher frequencies there. But on the other hand, we know that the fin whale population is increasing, whereas the blue whale population is not, and that's another puzzle. I should add to that the fin whale, when I say the population is increasing, my understanding is that it mostly comes from immigration rather than actual birth and death rate.
Yeah, I tried to look up that paper, and it looks like the fin whale, it may look stable because it looks like their song changed from predominantly single unit songs to doubles and triplets, which would be double the amount or triple the amount of song units being sung. So I was just starting to think, which would be kind of cool. So
I see what you mean. That would then, yes, that would increase the average amount of energy in the water by doing that, and that would increase the average levels. Yeah, well, that's certainly very relevant. Thank you.
Yep.
I think, Michael, there's a question in chat about inquiring about what the depths of the hydrophone deployment were, and are they consistent up the coastline?
Are they consistent? Sorry, the second part with?
I think the question was, are the depths of the hydrophone deployments consistent across the array?
Oh, right. Well, they're all. I don't know the precise depths of this equipment. The only information that's available to me as because it needs to be unclassified. The information, in other words, the actual depth is classified, is what I'm trying to say, as is the precise locations. That's why I was a little bit vague about where precisely these stations are located. But they're basically in the SOFAR channel, and all four of them are in the SOFAR channel. And they're designed to pick up long-range sound, distant sources.
Thank you. There was a follow-up statement to Jen's statement a moment ago, provided by Shyam, that says apparently the temporal spacing between, I think you guys were talking about fin whales at the time, the temporal spacing between units in a song is also increasing over the years. I don't know if that was a comment that was posted.
Right. Okay. So the gaps between the songs are increasing. Right. Okay. Yes, that's also relevant. So I didn't know that. Thank you. Other chat. going to be recorded, by the way.
Yes, we can export those if there are additional questions. We're trying to field them as they come in now. So
yeah.
Other questions from the audience?
I have a question, if that's okay. I've seen in some papers talk about ship quieting technology. Do you think that factors at all into that decrease or stabilization, just because ship noise does bleed into different frequencies?
So it's really hard to tell from this data set. That's primarily because my belief is that the slowdown occurs mainly in frequencies which are not dominated by ships. But having said that, I have seen multiple publications, including yours, which show a similar effect all the way around the world at similar frequencies, and in places where I would not expect them to be dominated by whales. So the impression that I have is that the sound from ships probably is not increasing at the rate that you'd expect from that graph. It's just that I can't deduce that from this particular set of measurements. And so, to answer your question, I think that quietening of ships probably does have an influence on those other measurements, but not one that we can detect here.
Michael, it's Terry DeVoe. I know you didn't want to cover it, but it strikes me not entirely unphysical that the total sound might be related to the square of the gross tonnage, because if in a perfectly frictionless environment, you would expect an effect linear with gross tonnage from the inertial mass, the energy required to move a larger inertial mass. And even in the absence of any inertial mass, just from the larger volume of water displaced, you'd expect a linear effect from, moving that amount of water out of the way as the ship moves forward. So since both things are there in real life, it wouldn't surprise me to be the square of the gross tonnage.
Okay, well, hi Terry. Thanks for the question. All I can say is that if you look at it from a point of view of linear acoustics, that this expression simply predicts a proportionality to the first power of the tonnage and not to the second power. Now, you're talking about moving water out of the way, dynamic machine, which would certainly take up more power, but I'm not sure that it ends up as sound. In fact, I think it doesn't end up as sound. That motion that you're describing.
Yeah, well, what I'm thinking is that ultimately it appears on the screw. In terms of power dissipation at the screw to move the inertial mass as well as to displace the water.
I understand what you mean now. Okay, and that if that were the case, it would manifest itself in the same equation as an increase in the source factor, because the propeller actually has to work harder to push the water away.
Right.
That's so you would, from that point of view, you might expect the source factor to increase with the tonnage. Now, okay, that's an important point, because I'm aware of the possibility that the source factor might increase with tonnage. I had no idea, I wasn't able to predict how it might increase. So for all the predictions I showed here, I assumed that the source factor was constant, not changed with time or with tonnage or any other parameter. I just assumed that the measurements by Wales and Heitmeyer were on average. I don't mean it's just accurate for every ship. I just mean that on average, they're valid for all ships and for all time. That source level has not changed with time, even though the tonnage has. So, that again is tied in. That assumption is tied in with Jen's question about the quieting. It is possible that the source factor would have increased had it not been for the quieting. All I can say is that I don't need to invoke any change in the source level in order to predict the measurements. I predict 5 dB based basically on the combination of the tonnage and the depth, because the depth increases with the volume of the ship. Tonnage is also proportional to the volume of the ship. So what you've got effectively is a volume to the power of 2/3. If you take the ratio of these two quantities multiplied by the number of ships, and that gives you the 5 dB.
Right, got it. Thanks.
All right. Any other questions? I do have one I can toss in there too, Michael, and maybe you kind of touched on this a little bit, but I was in a talk last summer at a virtual meeting where one of my terrestrial bioacoustics colleagues was talking about how the shutdown related to COVID had altered kind of patterns of birdsong in certain places. And so I'm kind of curious from a marine standpoint, has the pandemic over the last year changed the shipping volume or patterns that would show up, you know, in recordings over the past year or maybe into the next year that would help kind of validate some of these assumptions about traffic effects or maybe increases in marine biotic activity?
Right. So I'm probably not the best person to answer that question. There are other people out there who have actually looked at this question and might have a better answer. One of whom is my co-author Rex Andrew. Another is Stephen Robinson. I don't know if either one, and Jen, perhaps you have as well. Is either Rex or Stephen out there to answer that better than I can?
I was going to say, I don't know that for sure, but we have a project that we just got data back for Avion, and that's something that could be specifically looked at in a different way, not just looking at COVID impacts, but how this would pertain to Michael's question. Michael, that's a great data set to look for that.
Yeah. Right. Okay. But I know that both. Yes, I agree. That would be good. I know that Rex and Stephen have both been looking at CTBTO sites and looking to answer this very question. And I have seen some preliminary results from one site that look to the uninitiated like a clear COVID signature, but the person who showed it to me didn't describe it as that. So I'll wait. I don't want to speak on their behalf. If they're not here, then all I can do is encourage people to ask those questions to Rex and Stephen.
Well, I'm excited to see, Jen, the new data and learn more about that. Other questions from the audience for Michael?
It's Roberto here from JASCO. Just a quick note. If we're interested in more collective data sets regarding the potential effect of COVID, IQOE Ed Urban has been collecting a large catalog of equipment which is in the water, has been in the water over the past year. So that may lead to some kind of a concentration effort, and maybe Ed will be a good resource to query on this for anyone interested. Certainly, we provided information about ADON and a number of other instrumentation that we've deployed. So maybe watch that space and see if anything comes of it.
Yes, thank you, Roberto. That's a better answer than I gave. That is true. So I think IQOE is a very good way of pursuing that question further. There are people working on it actively.
I see a comment in the chat box from Krista that says that through the ECHO program, they are considering a project to look at COVID effects in the Vancouver region as well. So I'm sure this probably is an idea that's found fertile ground across study sites. So. All right, any other questions?
Yeah. Hi, Bruce Martin here, again from JASCO. Michael, I'm wondering if you've thought about trying to put in the energy density from seismic which has been increasing since 1990 as well, to try and figure out if that has an effect, or is it just not enough compared to the ships?
I don't think in this part of the world that there's much to speak of. My understanding is that it's that in the Atlantic it's a big deal, and if it's been in the Atlantic, I would have paid close attention to it. In the Northeast Pacific, my understanding is that it just doesn't happen. But I'm happy to be corrected if people know otherwise.
I think you're probably right. There isn't a lot there. I was wondering about, whether it could get around from the Atlantic or from other areas.
Well,
maybe
that's
not.
kind of hard. It can't exactly get across the Panama Canal. So I would say it's well insulated from Atlantic. So, I mean, there are sites elsewhere in the Pacific, for example, around Australia, and maybe further north. I don't really know. But I don't think even Australia, it's not the right coast. I think it's the northwest that's there's most exploration. It's really hard to think how the sound would get from there to the Northeast Pacific as well. So I haven't given it much thought, but I don't have any reason to believe that there's much seismic.
Yeah. And by the way, maybe a pet peeve of mine, but when we're talking about global phenomena like this, we should use the term seismic surveys rather than seismic, because that should refer to earthquakes.
I agree.
All right. Any other questions for Michael or comments? I see a couple of comments in the chat box about additional work being done on that topic of kind of COVID effects on traffic and noise levels. So appreciate those comments. If not, I will again thank Michael for taking his time out in the evening, as it were, in the Netherlands to share his science with us. Michael, everybody give him a round of applause there. I will take just a second to mention that we'll be having next month, March, the second Tuesday in the month. I believe that's the 13th or the 9th, actually. We'll be having another speaker in the series, Dr. Norman Lee from St. Olaf College, is going to kind of talk a little bit about auditory function and noise, I think using frog models this time. So we'll jump from the depths of the ocean to freshwater ponds for our next seminar series. So again, thank Michael for a great presentation, and thanks for joining everybody who logged in this morning. I think I saw up to 60 at one point. So appreciate it, and we'll see you all next month.